everyone, Peter Selby here, back again with another video on Peltiers, and I'm actually in the middle of a longer video on Peltier fridges, as well as just having a bit of fun trying to cool these guys down a little bit quicker than a conventional compressor-based fridge. But while I was making that video, I rediscovered a mathematical quirk that I'd kind of forgotten about. The reason I've forgotten it is because I'm doing so much high power stuff now where you need low thermal resistance to get that sort of heat from one place to another. But a Peltier fridge, especially this kind of form factor here, you're really stuck with high thermal resistances, and that's where this mathematical effect, a kind of quirk, comes back into play. It's the reason why, well, I think it's the reason why most manufacturers of these fridges have just got off on the wrong side. They haven't understood this quirk, and they're using 5 to 6 times more power than you actually need. Not this guy, by the way. This is one of the good ones. It's been designed with very, very low power for what it's doing. So I thought I'd just concentrate or make another video that's just concentrating on that point. I think it's such an important point. And for this, I'm going to be a little bit lazy. I'm going to use ChatGPT as a cheap text-to-speech synthesizer. I really struggle with that word, and the reason is because I do struggle with words, so I'm going to use that to generate the dialogue. I'm giving it the dialogue, so don't worry, it's not generated by AI. That leaves me more time to just play with the graphics with this. So that's it. I know you're probably confused about what this is all about at this stage, but that's because I don't want to let the cat out of the bag too early. So hopefully it will be interesting, and I'll see you again at the end of the video.
So there's a guy named Phil that wants to make a Peltier fridge. He follows the classic design of fitting a heatsink and fan on the hot side of the Peltier, while the cold side is bonded to a metal plate at the back of the chamber. The chamber is insulated, and the whole thing enclosed in a box to house the fan and a 12-volt power supply. When he connects the 12-volt to the Peltier, initially it draws 72 watts and cools the metal plate quickly. As things settle down, the input stabilizes at 12 volts, 5 amps, and 60 watts, while the midpoint in the chamber also drops to 3.5 degrees in a 25-degree room, about 21 degrees below ambient. Phil checks the Peltier datasheet just to make sure everything makes sense. He knows the Peltier itself is running at a large temperature difference. The hot side is 76 degrees, while the cold side is negative 1.5, so at that large DT, Peltiers are not expected to be efficient. Phil designed the chamber to have a thermal resistance of 5 degrees per watt, so you only need a few watts of cooling to maintain a low temperature. For example, 4 watts is enough to keep it at 5 degrees in a 25-degree room. Since he achieved 21.5 degrees below ambient, this suggests he's actually getting 4.3 watts, so a COP of 0.07. Not great, but in line with expectations for Peltiers, which are notoriously inefficient. He also knows the datasheet curves are monotonic. Well, actually, he didn't know that word, but he knows that increasing the current should increase the cooling, while reducing current reduces cooling. At the same time, the input power increases with current squared, so he knows that he needs to avoid pushing the Peltier much harder. Just in case, Phil connects up a laboratory power supply and stabilizes everything at 5 amps. He then reduces the current to 4 amps and finds that the cooling does reduce. The chamber temperature rises quickly. Eventually, it stabilizes at around 10 degrees, which is only 15 degrees below ambient. He repeats the test, this time going from stable conditions at 5 amps and then changing to 6 amps. As expected, the cooling increases, but the power jumps up to 86 watts. He worries about the heatsink temperatures and quickly abandons the test. In the end, he's confident that the 12-volt, 5 amp, 60-watt condition is just right for a Peltier fridge. Later, Phil bumps into his friend Peter that knows a bit about Peltier devices. "G'day, mate," says Peter. Peter looks at the design, goes away and runs some simulations. When he returns, he says, "Looks good, but did you know you can get exactly the same cooling with just 2.3 amps and 15 watts? Phil says, "No way, that's impossible." He starts spouting ZT numbers, the Carnot theory, the second law of dynamics, scientific papers, and just, well, everybody knows Peltiers are pretty bad. Peter says, "Come on, mate, no harm in trying." So they set up the fridge again at 5 amps and allow everything to stabilize. Then the current is dropped to 2.3 amps. Initially, things look bad, but after a while, a shock result. The chamber stabilizes at 3.4 degrees. "Okay," says Phil, "what's the deal?"
Well, it's all to do with parabolas. If you look at the curves in the datasheet showing the cooling power versus input currents, these are actually just the first half of a parabolic curve. The interesting thing about the full curve is that it has an apex, and on either side of the apex are two currents that get exactly the same cooling power. Of course, it would be crazy to use the current on the right side of the peak, as the efficiency would be horrible, like using 500 watts to get 50 watts of cooling. So the manufacturer, quite sensibly, only shows the first half of the curve. The thing is, when you use Peltiers in real-world applications, especially ones with high thermal resistance, that parabola does two things. It moves down quite a bit and also moves left towards the origin, which means now the apex of the curve can be well inside the typical range of currents, say from 1 amp to 6 amps for an 8 amp Peltier. And that means there can be 2 points in that region that can get exactly the same result. When I ran the simulation, I found the apex of cooling was at 3.6 amps and that 2.3 amps had the same results as 5 amps.
So what you were saying is that I'm running my Peltier fridge in the crazy region? But what about the tests I ran comparing 5 amps against 4 amps and 6 amps?
That's a common issue with Peltier systems. They have a few different thermal masses in there that can take a while to settle down, and it can create what's called a second-order response. This means the short-term change can move in the opposite direction of the long-term result. Kind of like a two-finger typist learning to touch type. There'll be an initial period of slowdown, but eventually you get faster. When you get this second-order response, it can be easy to get tricked by the flat point of the curve into thinking everything is stable. But really, it's just the system getting ready to head towards the final point of stability. It's an easy thing to get tricked by.
So what you're really saying is all the experts out there, the Wikipedia articles, the published studies, and manufacturers of these Peltier fridges just got it wrong. They're all running in the crazy region.
Well, I did find one fridge that seems to use the sensible region. When it first turns on, it does use about 60 watts, but it's not crazy at that point because it's charging up all the thermal masses in the system, and they have good thermal contact with the Peltier. So it's more like the datasheet Parabola. But once the cold side is down to temperature, it has an algorithm that adjusts the current into the sensible zone. So obviously I'm not the only one that figured this out.
So thanks to Peter and Phil there for that hopefully clear explanation of how people get off on the wrong track for Peltier fridges and any application that has relatively high thermal resistance. Now I've got 3 other quick subjects that I want to cover here before the end of this video. The first is that I have no affiliation whatsoever with the makers of this fridge. I've bought 3 Peltier fridges in the last 5 to 10 years. All of them have been power hungry, okay for their kind of cooling, and they all died after 1 or 2 years anyway, so not very good quality. Then my younger son bought it for my older son as a birthday present, and I was like, oh no, it's going to be the same thing. I was really shocked to find that it was like 10 watts for its long-term energy consumption, so very low. I thought, well, maybe it doesn't actually do anything, but I checked inside and everything was nice and cool, especially the walls inside here. Of course, the back will be nice and cool, but also the walls inside here I found were nice and cool. So yeah, it's a nice little fridge. Now, if you do get one of these, and it is a good quality one, so don't do the usual trick of just jamming a whole bunch of cans in there at room temperature and then seeing what happens. The thing is, this air, liquids and stuff, just not very good thermal conductors. It'll take a long time. It could be 1 or 2 days to actually get down to temperature. Compressor-based fridges have some tricks up their sleeve. They can create temperature difference, larger temperature difference, get some circulation going there, maybe fans and baffling and stuff like that. So they can cool things down a little bit quicker, but it still takes hours in a normal compressor-based fridge. But this guy here, just that circulation isn't there, so it is going to take a long time. If you do just buy your stuff from the grocery store, stick it in there, that'll be fine, or pre-chill stuff in your other fridge, that will work fine as well. But they're great. Once they're down to temperature, it will keep it at temperature for a very long time. So if you want to know whether or not you've got a good one of these or not, I think the best way is to just plug it in. This one here, it consumes about 60 watts when you first plug it in, but after about 10 or 15 minutes, if it's empty, it will go into that lower power mode, so that's probably a good way to tell. All right, the next subject was the formulas. So I kind of stayed away from any heavy mathematical stuff in the main bit there, but In a previous video, I've introduced a formula for Peltiers on their own. It's QC equals alpha Ti minus a half I squared R minus K dt. And this formula is just for the Peltier. And if you look in any scientific literature, you'll find this formula pop up all the time. The thing is, no one seems to rework the formula or just take into account the thermal resistances for an in situ calculation, which you can quite easily do. Yeah, I'm going to put it up on the screen there. It looks a bit gnarly, but that's only because there's lots of components in there. You've got the thermal resistance on the hot side, the cold side, and then between the chamber and the outside world, plus that the thermal resistance of the Peltier itself. You can get numbers for all of those. You can do experiments and figure it out. And then once you do that, put the real numbers in there, it comes down to something quite simple. So, it's really not that hard. If you're a STEM student at high school, the maths for this is well within the scope of what a high school kid could do. So it doesn't require a university degree to cover this at all. I have looked into the papers, and they go into a lot of weird stuff with second law of thermodynamics and entropy and stuff like that. It's totally, of course it applies, but it's totally useless for actually figuring out what's going on. They never do the proper analysis with the thermal resistances in situ. So it's just kind of crazy what I see in the literature itself. So I'm looking down here at a checklist to try and keep me on track. What I do in addition to, normally I never do the formula kind of stuff. I just use circuit simulators. That'll get me the heat flow and the temperatures and stuff in there. So I use an electric circuit simulator that's using electrical components to represent the thermal characteristics of the situation here. So not that hard to do once you've done it a few times. I'll probably do a video on that later. But the point is that it's a quick and easy way to get the numbers. With that particular circuit, it's possible to see what's happening there with the 5 amp mode where Phil was started off at in that previous section there. So with that 5 amps, you're probably getting somewhere around 90, 100, even 120 watts of core cooling. But because of the high resistance in the rest of the circuit, that core cooling is just going to circulate inside the Peltier itself. And this is something that a lot of people say, Peltiers are bad because it just ends up circulating inside. And you only end up with about 4 or 5 watts of cooling coming out the side here at the back of the fridge there. So that's kind of really, really wasteful. But it's not just wasteful for that core heat pump effect there. It also creates very high temperatures on the hot side. And that simulation showed that the hot side of the Peltier was getting to 78 degrees. That's probably okay for the Peltier itself, but the thermal paste is just going to evaporate away at that temperature. And especially if you've got a bit of thermal cycling going on, maybe you use it sometimes or not, or the makers have a thermal switch where they turn the Peltier on and off, and everything's sort of expanding and contracting and so on. Eventually your thermal paste is just going to just evaporate and disappear. So that's why the fridges were dying, so it's not very good. The third subject that I wanted to cover is my experience or how I know about all this stuff. So in my case, I was playing around with Peltiers probably, 3-4 years ago, because I was pulling apart these fridges that weren't working. And I had a lot of projects that just failed miserably. And eventually I decided to make a much simpler project called a butter cooler. And the idea was to try and keep the butter around 18 degrees, even though the room temperature might be 25 or 28 degrees. So it should have been a fairly simple project, but it also failed as well. So eventually I kind of got really frustrated. I looked at the literature, and the literature was like all this entropy and all this stuff that it just didn't really make sense. My engineering instinct, though, was that this should be a simple project. Simple problem. So I attacked it by doing my own or creating my own model. At the time I didn't use electrical components or anything. I was just using maths to model the different parts, and that eventually showed that squared or that quadratic equation. And when I solved the equation, I found out that the currents that I had been using in my original tests were just way into this wrong side of the parabola, and so I backed it off down to the other side. It was just a tiny amount of energy that it needed, and the whole thing worked. So at first I thought this parabola bit was really important, but it turns out once you move into the higher power area, you're also way away from the other side of the parabola there, so it became less and less important as time went on. But that was the original start of me being able to model Peltiers. Eventually I've realized how my model kind of fits in with the model that the literature has, that formula for QC there. But yeah, it was my kickoff for this whole thing. So I think that's it. That's the last item on the list here. Hopefully all of this was interesting and you've learned something, and I'll be back again in the future with that video on the deeper dive into Peltier fridges. All right, see you later.